Hi, I'm Brian Hamilton, and welcome to this recorded tutorial. This tutorial on finite difference time domain methods for acoustic simulation. So, um, this is a quick outline of my talk. I'll try to wrap it up in about 25 minutes. So I'll just quickly introduce the problem, room acoustic simulation, talk about different room acoustic models leading up to wave-based models where we find finite difference time domain method, numerical method for solving the wave equation. So I'll go through some details of FDTD methods, practical for room acoustics, and then conclude the talk. So we're talking about room acoustic simulations. This is useful for predicting, analyzing, and fixing acoustics in rooms. For example, mainly focusing on reverberation times or other metrics. And this can lead to oralization. So oralization is useful to listen to acoustical solutions. And this is also useful in virtual acoustics. So that could be video games or virtual reality applications. So these are the areas where room acoustic simulation is of interest. Room acoustic simulation mainly involves some sort of computer geometry model of a room, which is just a bunch of surfaces, triangles, and materials. And from that, we want to simulate or extract an impulse response at the most basic form. There are different room acoustic models. Just to put the wave-based or wave model into context, we'll start from the simplest models, diffuse field equations. So that's Sabine's equation or the Ehring-Norris equation, which relates the volume of the room. It relates the reverberation time to a ratio of the volume of the room to some measure of absorptive surface area. And then a bit more complicated than that, you have ray or particle tracing, which is, you can shoot out a bunch of rays and let them bounce around the room, where you have energy absorbed at wall reflections. And you can take an average decay of all these rays and, estimate T60s. Under diffuse field assumptions, you end up with, in fact, the Ehring-Norris equation. Or you can collect these rays or particles at a receiver volume and build up an impulse response over time, which you can use for oralization. Maybe a step in complexity beyond that is wave simulation. So here we simulate wave propagation at every point in the domain. And this typically involves setting up some sort of mesh or grid of points. And this produces some more, detailed behavior, but it also ends up being a bit more costly. So a kind of long-standing question is, which kind of simulation should you use? Waves or rays? Or what kind of model should you use? There's not really one answer. They both have their advantages. In certain cases, they can give similar results. In other cases, different results. Wave simulations tend to be expensive and slow. That's because they offer a bit more information than ray simulations, mainly diffraction. Diffraction is very hard to simulate otherwise, and that's a natural feature of wave models. So they include diffraction, they include all kinds of geometric behavior, and they include modal effects. So in fact, they're physically valid in the entire frequency range. That doesn't mean that the solution is correct or it's going to match, measurements that you make in the real world, but the physics are valid for the entire frequency range in your model. Ray tracing or ray models, geometric acoustics are more useful for quick simulations, so you can get quick results, quick predictions of T60s, or quick relative to wave models at least. The problem is, diffraction is very difficult to simulate in ray models. So there are some solutions, some very some solutions you can use for diffraction around edges, but quickly they start to be inapplicable to real-world scenarios, or they become quite costly to simulate all the different diffraction events. So that's the main challenge with ray tracing, which means that in low frequencies, they're less and less valid because diffraction is more important in low frequencies. So we can say that, of course, they're high frequency approximations. And that doesn't mean that maybe they won't give good results in mid or low frequencies. It's just physically, they are high frequency approximations. So at this point, we can jump into FDTD. So FDTD is a numerical method that simulates the wave equation. The wave equation is a wave model, of course, for rooms, or at least when we couple it with boundary conditions. So we'll start off with, we'll mainly focus on the wave equation in 2D. 2 dimensions kind of illustrates all the basic concepts of FDTD. For 3 dimensions, 3 dimensions is just a bit hard to illustrate. So we'll focus on 2D. So here we have U is our scalar field, our sound field we'll call it. It could be pressure or an acoustic velocity potential. It doesn't matter too much for this talk. C is the speed of sound. This term here is a partial derivative with respect to time, second order. And then we have partial derivatives, second order partial derivatives with respect to x and y, spatial coordinates. We're going to approximate this spatiotemporal function on a grid, on a spatiotemporal grid, with time step, or the grid spacing in time being delta t, and then we have a grid spacing in x and y, delta x and delta y, and then we have integer coordinates that kind of step us through the space. So n is the time step, or the time index, L is the x index, and m is the y index, integer index for the grid. So now we can actually approximate partial derivatives with finite differences applied to our grid function. So we have these integers here which tell us where we are on the grid in space and time, and we can change these numbers here to get different approximations or different points on the grid, and ultimately what we have here is a second order finite difference in time, which approximates this second order partial derivative. And we have a similar one in x, so here it varies over the L coordinate index, and here over the m index, which is the second order derivative difference with respect to the y coordinate. So we'll make some simplifications. We'll choose the x and y grid spacings to be equal, and then we'll set the time step based on the grid spacing and speed of sound. This ratio set to square root of 1/2. So this is known as the Courant number, and we choose this for stability reasons, which I won't talk about too much for lack of time. But under this choice, we get a very simple recursion. So this is basically this equation with this choice of grid spacing. We get some cancellations, and you end up with this simple equation. And what this tells us is that we can calculate the sound field value at time step n+1 based on previous time steps and spatial neighbors. So this is a stencil operation that visually looks like this. We're updating this point here, ULM at time step n+1, based on its neighbors at the previous time step, spatial neighbors at the previous time step, and its value 2 time steps ago. So we apply this stencil operation at every point on the spatial grid at time step n+1, and then once we're done that, we can just kind of move forward to the next time step, and we can kind of leapfrog forward in time. And that's how FDTD works. You do the stencil operation at every point on the spatial grid, and you move forward in time. So let's put this into practice with a very toy example. We'll consider a box in 2D, a rectangular domain, 10 by 4 meters. I've chosen some grid spacing, and I've laid out a Cartesian grid of points. So this box is oriented with the Cartesian grid, which is convenient. Now, the first thing we need to do is figure out which points are inside the grid and which points are outside. So that's very simple because it's a box. So here we have the green points are inside and the black points are outside. And what we're going to do is simply apply that update equation that we derived to the green points, and we'll just leave the black points as set to 0. Okay, so implicitly this is our boundary condition. U is equal to 0 at the boundary. And if we look at what happens, we get wave propagation, reflections off of walls. But if you look more closely, what you'll notice is that we get phase inversion at the wall reflection, which is not what you want for a room. This is in fact what you would see in a membrane. So we're simulating a membrane, not a room. In a room, at the very basic, the most basic model, you would have free boundaries. So we need to do a bit more work to get that. So free boundaries correspond to rigid walls. We need a new boundary condition for this. Now we have a boundary condition which is in terms of the spatial derivative, and that's in the direction of the normal vector at the boundary pointing outwards. So that's this n hat. And this can be discretized with finite differences and substituted back into our update equation. And what we end up with is a more general update equation, which looks like before, but now we have this extra term here, 2 minus 1/2 k L of m. K L of m is an integer between 0 and 4 that represents the number of interior neighbors. So for a point that's well in the interior, we have 4 nearest neighbors on this Cartesian grid. And then you have 2 minus 1/2 times 4, so that disappears and we end up with our update equation from before. At the boundaries, you have 1 less or 2 less, in this case, interior neighbors. So we have 3, k equals to 3 at a wall, because 1 point falls outside, and at a corner we have k equals to 2. So this is activated at the boundaries, and we'll leave the outer nodes to 0, so this happens to work out. And we get the same kind of wave propagation, but now with phase preserving reflections. So we don't have a phase inversion like we had before. And you should pay attention to the axis here, because next we'll add decay and we'll see that it actually goes down over time. So this allows us to simulate room modes, but in a real scenario we have absorption in the room. There's 2 types of absorption that you have in room acoustics, typically air absorption and wall absorption. I won't be able to cover air absorption, but we'll cover wall absorption, or a very simple case. So we need a new boundary condition. This is a locally reactive impedance or admittance condition. So it looks like before we had a rigid, this was in the rigid condition where this was set to 0, but now we have gamma over c and then a partial derivative with respect to time, first order one. And gamma is now an admittance, and it will relate to the absorption at the wall. So we can discretize this with finite differences. Again, we choose finite differences such that, I make a particular choice. This choice is made based on stability considerations, which I won't talk about. But we can substitute this boundary condition back into the update equation and end up with an even more general update equation, where in this case now we have 2 extra terms which are linked to this gamma constant. And you can notice that on the interior, when k is equal to 4, we have this thing disappearing and this disappearing and this disappearing, and we end up with the usual interior update. If gamma is equal to 0, this disappears and this disappears, and we have the rigid update. And if gamma is greater than 0, so if gamma is less than 0, it doesn't work out, this is unstable. But if gamma is greater than 0, then we have absorption. And the absorption is linked to the reflection coefficient at the walls through this equation. So this is the normal incidence reflection coefficient. And here I've chosen r equals to 1/2, which means that when a wave hits the wall, it will reflect back with half its amplitude. So if we look now at the behavior, we see similar behavior, but In fact, if you notice here, we've gone down by about a factor of 10 in amplitude over those few time steps. So I'll just play this again. So if we notice here, you can see the reflection from the top and bottom walls are kind of at a much lower amplitude than the waves going left and right. That's about all there is to show. Okay, so now we can move on to a more complicated geometry. So all I've done here is added a dome, a circular dome to the scene. And in this case, it's actually, so we have to go back to the first step, which is to figure out which points are inside and outside. And in this case, it's easy to do that because I've chosen a domain that's the union of two convex domains. So we can just say, is a point inside this rectangle or this circle? So the circle would extend like that. Sorry. So if it's in either of those domains, then it's inside the room. And we can just run the same update equations, and all of a sudden we get, more complicated wave phenomena. In fact, we can see, complex diffraction effects, which, and I say they're complex because they would be quite complicated to simulate otherwise using array-based method. So we have diffraction at these corners, interior corners, diffraction on this curved surface. So these are very challenging things to simulate in geometric acoustics, but in this case, it was kind of a short step from the box simulation that we did before. Now I'll take a slight detour and focus on the problem of figuring out which points are inside or outside. So that's sometimes called voxelization. So each point represents a voxel. So I've considered this scene, which is, the union of convex domains, but let's say that we can't break up this room into convex domains and we need a more general technique to figure out which points are inside or outside. Well, we can do this by using the Jordan curve theorem, which basically says that if you have a closed curve or a closed kind of manifold, then it divides the space into two regions, in and out. And that means that you can kind of shoot a ray through this domain, and you'll always pass from inside to outside, no matter what direction you shoot the ray from, as long as it's closed, so there's no holes. So we can use this to classify the points as in or out by simply shooting rays, and these are conceptual rays, not acoustic rays. We shoot rays along the grid points, and then we mark the intersection points with our domain, and we can classify points as outside and then inside and then outside, and we can just keep alternating like that. And that works from any direction. So you can just go along all the different rows and in one direction and classify all the points. Now, there are a few issues that can arise in this approach. If you're hitting corners, you might not get the behavior you expect, especially in 3D. These intersections may not be defined at edges or corners. And due to finite precision effects, you could get hits or could not get hits. In this case, if we registered a hit at every one of these kind of, corners, I'll call them corners, we would go from outside to inside. That's fine, but now we're back to outside along this line. And if we mark those points as outside, we would actually divide these two regions. We would separate them, and that's not obviously what we want. So I would call that a catastrophic error. So there's a problem with this algorithm, which is, it has global effects on the grid. And, you might want to think about treating those special cases carefully, or maybe moving to some other algorithm that is more localized in its effects. So that's just one of the complications that arises in setting up finite difference schemes. In terms of the Lossy update, there's something else I'd like to mention, which is kind of interesting. You can take this, and we've kind of talked about this, how the different updates appear in this equation. So you can actually break this up into two steps in the Lossy case, where you have a temporary variable which represents the rigid update, and then you can simply, so that one looks at spatial neighbors. And then in a second step, you can kind of correct it, update it, without looking at spatial neighbors and just kind of bringing in the previous point. So, it might help to break up these two steps for your for your computer architecture. It might be more advantageous to do these in two different steps. And in fact, you can take this update here and generalize it to do frequency-dependent losses without changing this update. You can also change the scheme, and this one kind of looks similar, so sometimes from a programming point of view, it makes sense to do this. And just the idea of separating out the specialized updates that you do at the boundaries. So rather than applying this update to every point in the grid, and especially when it can get more complicated with filters at the walls, you might want to isolate the boundary points and treat them on their own and use a more simplified update for the interior points. And the thing here is that the boundary updates can get more and more complex, but that in the limit of small grid spacings, the number of boundary nodes, or the nodes that are next to a boundary, goes to 0 relative to the number of interior points. So that's going to be true in 2D or 3D. So it usually makes sense to kind of treat the boundary points as a separate step. In terms of, you might have heard that FDTD is, a very good algorithm or a method to parallelize. So that's true because it's a data parallel algorithm. I mean, in the case of an explicit update like we chose, implicit schemes are not so parallelizable, but we've chosen an explicit scheme. So basically, the update at this point can be carried out independently of the updates at these other points, and so they can be done in parallel. So it's a data parallel algorithm, and you typically have large data sizes. So because the grid, in 2D or 3D, as you reduce the grid spacing, the points go to the power 2 or the power 3. So you quickly end up with many, many points. And this is great for parallel execution because it just, there's always overheads you have to, serial parts of the algorithm that you have to overcome. So the other thing to mention is the arithmetic intensity is low, and this is specific to certain parallel architectures, but this basically means the number of operations that we have to do at each point is small relative to the number of the amount of data that we have to read in to update a certain point. So you could imagine those update equations could have ended up with many, many steps, multiple iterations for each time step. So we could have increased the number of floating point operations while keeping the data reads constant. But in this case, it's a very simple update, and so it's got a low arithmetic intensity. And that's useful for graphics processing units, or GPUs. For example, NVIDIA GPUs with the CUDA framework. Because the arithmetic intensity is low, they tend to be memory bandwidth limited rather than flop rate limited, so floating point operation performance, limited. So they're limited by the bandwidth of memory. That's the, how quickly you can move memory from, global memory to the execution units or the cores on the GPU. And you might know about Moore's law, and you expect exponential growth in the performance of computers, but in this case, memory bandwidth tends to be increasing linearly at least over the past decade. So that's a good thing. Linear increases still means it's improving, but it's not exponential growth as you would, or increases as you might have thought. So over time, these algorithms get faster and faster to run. So this is the last thing I'd like to show, which is basically some quick benchmarks within MATLAB using a GPU and not using a GPU. So what I've got here is a speed up factor for different grid refinements. So I'm using that dome-shaped room that we saw before, and I'm just increasing the number of points by refining the grid by some power of 2. And then we're measuring the speed up of the GPU over the CPU. So that's the amount of time it takes to run a certain number of time steps on the CPU versus the GPU. So greater than 1 is good, and higher is better. And I'm also reporting the GPU utilization. So how much of the GPU are we saturating, or how well are we saturating the kind of utilization of this GPU? So basically what this is showing us is that as we increase the number of grid points, or as we refine the grid, the GPU performs better and better relative to the CPU. So at the highest at the highest grid refinement, we end up with 100 times speed up between the GPU and the CPU. And this is still within MATLAB, but I'm using CUDA, calling CUDA from MATLAB. And for low numbers of grid points, you end up actually with the CPU beating the GPU, and that's because the overheads of using the GPU are too large to actually get any gains. And you can see kind of that this speed up trend follows the trend of GPU utilization. So ultimately, to get good performance with the GPU, you need to saturate its cores or bandwidth channels, memory bandwidth channels, so that it has enough work to do and you can get good performance on it. So GPUs tend to work really well when you have a lot of grid points, and that's very quickly happens very quickly in 3D. So for this, just to be clear, I used this E5 2687W CPU, which is quite old now, and 1 core. So you can imagine actually there's the possibility of using 8 cores or 16 threads on this CPU. So you could end up with 16 times. We would have to divide this by 16 at best with the CPU, but we would still end up with gains for the GPU and high grid numbers of grid points. And in fact, you can still get even better performance both in the GPU and CPU if you run these algorithms outside of MATLAB. And so the GPU was a GTX Titan X Maxwell architecture. There are open source implementations available for FDTD and 3D. So here's a few. The main one I would recommend right now is Parallel FDTD, which is from Aalto University. It's been it was developed in 2014, but it's been updated recently to make it a bit more easy to install, and it's updated for Python 3. WaveRib is another one that's interesting. So this one works on NVIDIA GPUs only. This one is coded with OpenCL, so it actually works on different types of parallel architectures, including AMD GPUs and Intel CPUs or any kind of CPU, multi-core CPU. There's the K-Wave toolbox, which is worth mentioning. It's not quite finite difference time domain, but it's similar. It's a pseudospectral time domain method. So it works on a Cartesian grid similarly, and can be used for acoustics. And if you want to run the simulations that I've run in this tutorial, I've put the code for that, the MATLAB code for that on GitHub. And that includes the GPU execution kernels. So if you have the parallel computing toolbox in MATLAB, you can, and an NVIDIA GPU, you can run the GPU version. So to conclude, FDTD is a promising technique for room acoustic simulation. I've covered a basic 2D model, Cartesian grid-based FDTD with simple wall absorption, and I showed that it's straightforward to simulate, scenes with complex diffraction, and it's well suited for GPU acceleration, and there are open source implementations available that you can use. And that's it. So there's my contact info if you have any questions. There's also should be the ability to ask questions on the conference, the e-conference platform, which I can get to later on. So thanks for paying attention to my talk.